In 1654, the German scientist Otto von Guericke conducted a theatrical demonstration of the power of the void. He pumped the air out of a hollow copper sphere and attached 2 teams of horses to pull the halves apart. They failed. The suction of nothing was stronger than 16 horses. At the time, this established our baseline definition of a vacuum, a total absence of matter. Modern physics has since discarded the idea of a truly empty void. We now know that a classical zero-energy vacuum, a space where absolutely nothing is happening, does not exist anywhere in the universe. Instead, space is filled with quantum fields. You can visualize these fields as an infinite grid of pendulums, one at every point in space. Because quantum mechanics is inherently uncertain, these pendulums never hang perfectly still. They are in a state of constant restless jitter. This means you will never find a field with exactly zero energy. Even in the deepest reaches of the cosmos, the vacuum has a minimum energy configuration called a ground state. Particles are simply ripples in this ever-present jitter. This energetic foundation dictates the rules of reality, determining which particles can form and how the laws of physics manifest across the universe. Most fields have one stable ground state, where they remain forever, but some scalar fields have multiple angles where their pendulums can get stuck. If a field is trapped in a state that isn't the absolute lowest energy possible, it's called a metastable or false vacuum. If our universe rests on one of these temporary foundations, it faces an existential risk. A random quantum fluctuation in one location could bump the field, causing it to finally drop into its true lowest energy state. This drop would trigger vacuum decay. A bubble of true vacuum would expand outward at nearly light speed, dragging the rest of the universe with it to rewrite physics as it goes. As the bubble passes, it would instantly dismantle the atoms and molecules in its path. The specific physical laws that allow our chemistry to function would simply cease to exist. Our entire reality is built on a specific variety of nothing that appears stable, but is mathematically capable of collapsing into a more favorable state. These quantum fields are more than theoretical. In 2012, experimentalists at the Large Hadron Collider proved that a scalar field, known as the Higgs field, permeates all of space. In the hot early universe, the Higgs field was in a different state. As the cosmos cooled, it froze into its current configuration. And it is this non-zero value of the Higgs field that gives many elementary particles their mass. But we don't know if the Higgs field has finished settling. Some theorists argue its current state, despite lasting 14 billion years, is only a temporary rest stop on the way to a deeper ground state. Physicists visualize this through an energy landscape. A field seeks lower energy by rolling downhill. The deepest valley is the true vacuum, but it can rest in a higher valley indefinitely. Our universe sits in one of these higher valleys, physically blocked from reaching the deepest point. This means the mass of particles and the very stability of our atoms are temporary conditions, dictated by whichever valley our quantum fields are currently resting in. The landscape becomes even more complex if the universe has extra hidden dimensions. String theory suggests these dimensions can fold in nearly countless ways, each creating a distinct vacuum with its own unique physical laws. This dovetails with the theory of cosmic inflation. Once inflation starts, it may continue forever, with most of space exploding outward, while small regions stop and form stable bubbles. We happen to live inside one of those bubbles. This helps address a major discrepancy. When we calculate the energy of all our quantum fields, the result is huge, enough to rapidly rip the cosmos apart. Yet the observed expansion of our space is extremely mild. Without a multiverse, the math suggests our universe should have been ripped apart long ago. If space is filled with trillions of different bubbles, our existence becomes a matter of probability. We occupy a rare, quiet region because the vast majority of other possibilities are far too violent for life to take root. In this view, our calm vacuum is not a unique design, but a statistical inevitability in a multiverse where almost every other environment is inhospitable. However, even a calm bubble can destabilize. If hidden dimensions exist, they introduce new ways for the vacuum to decay. Physicist Edward Witten found that quantum jitters can cause a curled-up dimension to shrink. If it shrinks to a point, it vanishes into nothingness, taking the rest of space-time with it. This would create a bubble of nothing, a rapidly expanding sphere with no interior. Its surface would mark the absolute edge of existence, where space and time simply stop. Recent calculations show that if these extra dimensions are large enough, our vacuum can survive for many billions of years. Decay is a long-term mathematical pressure, not an immediate threat. Our existence depends on the specific, fragile way our vacuum is currently folded. But as dimensions fluctuate over trillions of years, physics predicts a shift toward the absolute ground state. In the end, the most stable version of nothingness is the one that contains no space or time at all.